Hey, so this is the first of many parts looking into what we call an introduction to modeling and looking at various functions. And while part of this lesson will be about linear functions and parts about quadratic, the vast majority will be about quadratic functions, which is a pretty big topic that I'm just going to go into a bit of detail here. With that said, though, first thing I want to talk about are piecewise functions and how we can define a function in pieces. For example, if you look at this function here, it's composed of two line segments, a line segment here and a line segment here. So how can you express this as an equation that puts all of this together? Well, first let's find the equations of these two line segments separately. So the part in blue, these are lines, and if I want to find the equation of a line, I definitely need the slope. So if I look here, I can see the slope. If I pick or the gradient from here to here, I can see I'm going down 60 and I'm going over 30, looking at the scale of my graph. So my slope is negative 60 over 30, or negative 2. That said, let's look at my other line segment. From here to here to find the slope, this is going down 60 and going over only 10. So this has a slope of negative 6, or no, I'll say negative 60 over 10, or negative 6. So now the equation of each of these lines. Well, if I define the equation of a linear function, if you know the slope and the y-intercept, which I can see right here is 120, I can find the equation pretty much right away. So if I write down an equation for y equals negative 2x plus 120, negative 2 being the slope, 120 being the y-intercept, that is the equation of a line that goes on and on forever. However, I only want this to represent part. I want an equation of only part of this. And so I need to have a restriction here where this function begins at 0 on the x, or actually on lowercase t, but I'll leave it for x for a moment, and ends at 30. This function only exists from here to here, 0 to 30 on the x-axis. So sticking with x and y for a moment, I would have a restriction where 0 is less than or equal to x, which is less than or equal to 30. Or actually, I'm going to make it just less than 30. I'm going to call 30 where we switch from one piece to the next. It doesn't really matter too much because they overlap there, but that there represents this. So now just a little bit more work is to find the equation of this line segment. Because the only reason this is a bit more work is because I can't see the y-intercept. But I don't need to. We learned earlier, or reviewed earlier, that any linear equation can be determined if you know a point and the slope. And so we call this point slope form or point gradient form. And it looks like this, where again, the slope we know is negative 6. And I know a point. I can pick any point. I'm going to pick this point right here, which is 30, 60. So that's like my x1 and that's my y1. And so looking at this equation, it won't be quite as quick, but I'll get y minus my y1 value, which is 60, equals my slope, which is negative 6, times x minus the x value of that point I picked, 30. I just want to clean this up a bit. Y equals negative 6x plus 180 plus 60, distributing the negative 6 and adding 60 to both sides. And so I get y equals negative 6x plus 240. And that there represents the equation that goes on and on forever for that segment in yellow. So now I don't want it to go on forever, so I need to add a restriction here. And this segment starts at 30, and I'm going to include 30 because I didn't include it for my other piece, and it ends at 40. So these are my two segments. So to write this equation in piecewise form and to use the equations that we were given, there was no x and y here. There's a t-axis, or capital T and lowercase t. So I'm going to say t, capital T, and I break it up like this. Actually, let me get myself a little bit more space here. And so I just write my equations out now. My first equation, the one I've highlighted in blue, is negative 2x, or sorry, negative 2 lowercase t, to use the variables given, plus 120, where t is between 0 and 30. And that's now that part complete. And for the other piece, it was negative 6t plus 240, where 30, we look at this piece from 30 until 40. So that equation there is an equation of piecewise form that relates to the graph here. And you can apply this to any function, any type of function. It doesn't have to just be linear functions. And before I move on, if I go to Desmos, if I just kind of zoom out here, we can see a similar graph. There we go. There is the same thing graphed in Desmos, and I graphed two separate equations here, but with those restrictions. All right, so the rest of this, I want to talk about quadratic functions. And without a graphing display calculator, I want to determine all these points here. And first, the x-coordinate of the vertex. So maybe let's do a quick little review of quadratic functions. All quadratic functions have a vertex. That vertex is either the maximum point or the minimum point. It is also the only turning point in any quadratic function. And the vertex, the x-coordinate of the vertex can always be determined by this, minus b over 2a, where b is the coefficient of the x term and a is the coefficient of the x squared term. And so in this case, if I want to find the x-coordinate of the vertex, I can do so quite quickly because that x-coordinate of the vertex must be the same as minus 8, that's my coefficient of x, divided by 2 times a, or in this case, 2 times negative 1. And simplify this down, I get 4. So the x-coordinate of the vertex is 4. The vertex is at 4 comma something. Well, the next thing is the y-coordinate of the vertex, which I can figure out by just taking this 4 and substituting it back into my function. Remember my equation here. If I know x, I can figure out y, the output. And now I know the x-coordinate of the vertex is 4, so I'm just going to substitute 4 into here. So really I'm finding f at 4. And so instead of negative x squared, it's negative 4 squared plus 8 times 4 minus 12. And if I do that, I get my y-coordinate of the vertex. And I should get exactly 4 as well. So now I know where my vertex is. My vertex is at 4 comma 4. I want to find the x-intercepts. Well, to find the x-intercepts of any quadratic function, well, one thing you could always try doing is factoring it, but I'm not going to talk about that here just because a lot of functions just don't factor. And I haven't reviewed factoring in this course, so while that is an option, if something factors, the quadratic formula always works, and the quadratic formula tells us the x-intercepts of a quadratic function. And so in this case, we'll remember the quadratic formula is minus b plus or minus the square root of b squared minus 4ac all over 2a, where again, a is the coefficient of x squared, in this case negative 1, b is the coefficient of the x term, and c is the coefficient of our constant. So in this case, I get negative 8 plus or minus the square root of 8 squared, which is 64. And keep in mind, if your b value is negative, it doesn't matter because you're squaring it inside the radical here. Minus 4 times negative 1 times negative 12. Just be wary. This part here is where it's easy to make a mistake. There's quite often a lot of negatives here, and this is a pretty common place for students to make mistakes. And all of this is being divided by 2 times a, so 2 times negative 1. So in this case, we should get negative 8 plus or minus the square root of, now everything you see highlighted under the radical here, or the square root, all that should come to 16. Which is a perfect square, which is a sign that actually this could have been factored. But again, I'm just going to leave it for now. But there's a lot more to do to clean this up because this is really the same as negative 8 plus or minus 4 over negative 2, which means 2 things at once, or 2 separate possibilities. It means negative 8 plus 4 divided by negative 2, and it means negative 8 minus 4 divided by negative 2, each of which are pretty nice values. We get for the adding one, we get one of them, we get positive 6, one we get negative 2. Sorry, positive 6 and positive 2. I'll write them in a different order, actually. So this here relates to this here relates to this, and those are our x-intercepts. So next, I want the y-intercept. Well, the y-intercept of any quadratic function is, well, there's a few ways of looking at it, but if you have your equation in this form, in standard form, the y-intercept is always the constant term. So the y-intercept must be negative 12. I'm just going to label it right here. Now, why is that? No pun intended. Because y-intercept for any function is the value, it's your output when you replace x with 0, because the y-axis is anywhere your x coordinate is 0. So if you substitute x with 0, every term that has an x becomes 0 and essentially vanishes. And so all we need to look at is a negative 12 there. And so there's our y-intercept. And so now I can sketch this graph. And so make a really quick sketch here. So what do I know? I know we have a vertex at 4, 4. I'll label that roughly right here. I know it has an x-intercept at 2 and at 6. I know it has a y-intercept at negative 12. Maybe I'll put that down here. And so I've got 4 points. I can make a rough sketch of this quadratic function. Again, all quadratic functions make a parabola. There's my quick sketch of f of x. Finally, what's the domain and range? Well, now that I have the graph, I can just see that quite clearly. The domain is going to be just all real numbers. All quadratic functions in general have a domain of all real numbers unless they're an applied question and the context of the question precludes certain values in the domain. But in general, you can put any number for x into it. The range will never be all real numbers. In this case, it's everything from 4 and down. So the range is everything less than 4. All right, crash course on a lot of things with quadratic functions there. Lastly, I have some details about a quadratic function and I want to figure out the equation. And the last thing I'll do is kind of confirm. In fact, maybe I'll do that here. I'll confirm that what I did was right here. So before I go on, maybe I'll switch back to Desmos. Turn this off and turn this on. This was the graph we just sketched. Notice the vertex is right. My x-intercepts, my y-intercepts. So yeah, we made no mistakes. Always good to check that. So lastly, I give some details about a quadratic function here. I tell you it goes through the points shown. It goes through -1, 5 and 0, 4. 0, 4 is a good one because that's our y-intercept. That tells us part of the equation. I also say it has an axis of symmetry at 1, which is still shown on here, which means that's where my parabola has the line of symmetry, which means 1 must be the x-coordinate of my vertex. So my vertex must be somewhere along this line. And in fact, I can tell my vertex must be somewhere around here because I can see I have something like this. And so somewhere around here is my vertex. I'm not going to put too much faith into my sketch here. And then I know it must go back up. Okay, so I'll just draw something like this. But I know this is roughly what this has to look like because the axis of symmetry is that point there. So I now want to find the equation of this and then use my graphing device to determine if it's correct. Well, first, any quadratic function can be written in this form, ax squared plus bx plus c, but that c is always my y-intercept, and I know the y-intercept is at -4, so I could just go straight to this and say ax squared plus bx minus 4. All right, so I got part of my equation. I need the rest of it. How can I figure out the rest? Well, let me look back at this point here, -1, 5. I know when x is -1, y is 5. So let's substitute those values into what I know about this equation. So instead of y equals, I'm going to write 5 equals a times, instead of x, I'm going to have -1 squared plus b times -1 minus 4. I know this equation must be true. And so let's clean this up a bit. I get 5 equals just a minus b minus 4. And I'm going to add 4 to both sides so that I get a minus b on one side and 9 on the other. All right, so I have 2 unknowns. If I can figure out another equation with both a and b, then I can put those 2 equations together and solve a system. But right now, I don't have enough information to solve this. However, again, we know the axis of symmetry is right here, which means we know the vertex has an x-coordinate of -1. And remember, we can find the x-coordinate of any vertex if we know minus b over 2a. Well, in this case, I don't know b and a, but I know that the x-coordinate of the vertex must be at 1. So I know this must be true. And now I have another equation with both b and a in it. So put this equation and this equation together, I can solve for a and b, and I'll know everything. I'll know everything. And so with that said, I would like to clean up this equation. I'm going to multiply both sides by 2a to make it a little bit nicer. So I have just 2a equals negative b, or add b to both sides. I have 2a plus b equals 0. All right, so I can now solve a system. A minus b equals 9, 2a plus b equals 0. I could solve this in many ways. I'm going to solve this algebraically because the equations are quite nice. If I just add these two equations together, this is called using elimination. If I just add these two equations together, I can see that my b's will cancel out. I have a plus 2a is 3a. I have minus b plus b is nothing. And then I have 9 plus 0 is 9. And so quickly I got 3a equals 9, which means a must equal 3. Everywhere I saw an a now, I know it's equals 3. So now to figure b, I can just substitute 3 into any equation that has a and b. I don't know, I'll substitute it back into this one here. So if I just imagine this equation here, now with instead of a minus b equals 9, if I imagine it being 3 minus b equals 9, pretty quickly I get to b equals negative 6. And now I have all the pieces I need. And so let me just write out the answer, and then I'll just double check that this fulfills all the requirements. And so now I can say my equation must be y equals, instead of a, I have 3x squared, plus instead of b, I have negative 6. So actually I'll write this as minus 6 times x, plus, or actually plus my constant, but my constant is negative 4, so I'll just put minus 4. So there's the equation. And to double check on a graphing device, let's just switch here. I'll go into Desmos, turn this on. This is this is the equation I just figured out. And just notice a few details. The vertex is at 1 on the x. It does have a y-intercept of 0, negative 4, and it does go through 1, 5 up here. So I am right. That's good. Probably shouldn't be teaching this if I wasn't right.